basically millimeter wave and terahertz and how they can be applied for 6G wireless and beyond. So the slides are actually longer, but I'll just try to see what I can cover in today's session. And please, you can stop me anytime if you have any question. So do ask any question if you have. Okay, should I start?
Yes, sir.
Okay. Right. So my network sometimes goes. So if you see a bad network, do let me know. I will try to see. Okay. Thank you. So today's talk is mainly taken from this key reference, which is a book chapter we wrote last year. So if you want to refer to any of the content, you can go to this chapter. It's freely available. And this work is co-authored by Shuchi and Nithin, which are my students, and Harpreet from Virginia Tech. So the outline of the talk is like this. We know that we are currently in the 5G standardization phase, and we are seeing that millimeter wave, which is a important part of 5G, it has becoming a reality very soon. So earlier it was thought that the millimeter wave propagation characteristics are not good, that's why it cannot be used. So despite of all this concern from about millimeter wave, about its unfavorable propagation characteristics, we are still seeing that millimeter is now becoming a reality. But as we go high, as we go improve our systems, our application are ever evolving. For example, we are going to see very soon very data extensive applications such as 3D gaming and extended reality and many other applications which requires very low latency and several hundreds of gigabits to terabits speed. So the question remains, will 5G be sufficient? Right? Can it support these kind of applications also? And that is the exact design goal as we look for beyond 5G. If you look at for 6G and even further generations, that is would be a goal to even achieve a higher speed, which is around gigabits or several terabits. So given the potential of terahertz communication system, which can provide, is a strong candidate that can provide very high data rate, uh, these are widely regarded as the next frontier of the wireless communication research. So the goal of this talk is uh, we want that all the audience get sufficient background about millimeter wave and terahertz bands. And we want to highlight why these bands are necessary for commercial application in the current landscape we can see. And we also want to explore what should be the key design consideration when we are going to design communication system in these bands. So we want to give, so there are multiple bands, there are little bit different technologies. So we want to give a unified treatment of these bands with a particular emphasis on what are their propagation characteristics, what are their channel models, what will be design and implementation consideration, what implication we can get, I mean, how we can envision these systems, how they would look like when they are applied, and what are their potential application to 6G standards. So we'll start with a detailed discussion of propagation characteristics at this frequency, and which will naturally move to how these propagation characteristics can be captured into channel models. When we are going to talk about this, we keep on contrasting them with the older bands, right? So that we actually know what is new. Most of you already know about the standard communication in conventional sub 6 gigahertz. So sub 6 gigahertz means the frequency which are below 6 gigahertz. So these frequency we have been using from a long time, so people are familiar with that. We want to make sure that we understand what are the key differences with respect to these frequencies. Then we explain what are the implications of these differences on design consideration or the implementation of these systems, what we need to change, what we need to take care when we want to apply, when we want to make communication systems operating in these frequencies. And if the time remaining, I will also want to have a look over what are the standard current standardization activities in these bands. So let me start the talk. Uh, I'll give a short introduction, which include a history of how millimeter wave and terahertz frequencies came into existence. Uh, so we know that this standardization of the current 5G radio was driven by the diverse throughput, reliability, and latency requirements of this ever-evolving ecosystem of applications. Right? So now we do not see in old time we used to have one or two applications, like we want to support audio calls, we want to look at probably a video call, but nowadays there's many internet applications which are coming which need to be supported, and that's how this Internet of Things concept came into picture. That we're not just supporting one application; these all applications are together, whether it's in health domain or it is in education domain, whether it's a call, commercial applications, or common surveillance. So these all application requires a diverse throughput and reliability and latency requirements. So, for example, you must be knowing about some particular application which are enhanced mobile broadband or ultra reliable low latency communication and massive machine type of communication. So these are different type of application which may have different latency requirement, different reliability, and throughput requirement. So one size fits all solution may not work for all these applications. You have to create a standard which can support all this variety of application via various mechanisms. So when we talk about the past generation of cellular standards, they have explored the use of advanced communication engineering techniques to improve the data rate and other communication reliability. So few important examples which we see, which past generation of cellular standards have used, is one is network densification, which means you keep on putting more and more base station in the network, right? Then you can, of course, increase spectral efficiency by using multiple antenna systems and doing some more tweaking, such as doing a smart scheduling and some other techniques you can use, right? But we have used many of these techniques, and some are still being discovered. But the one thing was realized in 5G, that classical, just using this classical sub-gigahertz spectrum and try to improve those with various techniques is not going to be sufficient to support the requirement of these emerging applications. We have to do something new, and we need a very different solution. And that's how people thought about using millimeter wave spectrum, which is above the current spectrum we are using. So we use mobile communication like standard around gigahertz frequency. Wireless and sub application are used around 2 to 5, 6 gigahertz frequencies, but people have not looked over beyond that. So the reason why these applications were basically thought that they are unsuitable for mobile applications. So you can have some application, right? You can have some fixed link application or non-communication based application using millimeter wave. But to provide a mobile operation, which require that you need to support users which may be moving, it need to be reliable, so people can you should be able to call from this at any time. So these applications, when we keep in mind, we it was thought that millimeter wave may not be a good option because its propagation characteristics are not good. Uh, it suffers from propagation losses and blockage losses. But the modern device and antenna technologies made it feasible to use these in commercial wireless application. They're going to talk about this thing. So we saw a first paper, or what I say, a very important paper, millimeter wave communication for 5G cellular. It will work, which kind of discussed in detail how these communication system may work with some design consideration. And that's how 5G standards took this commercial millimeter wave communication as a main agenda in their standards. But now, as we look into future, it's evident that even when we have more application like augmented reality, ultra HD video conference calling, and various data hungry application, and even some health application, we require even more, I mean, orders of more throughput and reliability requirements. And also we raise a different field, which we known as nanoscale communication. So nano is a very small length, and the nano devices, when they are deployed, they may need to communicate with each other. So for this application, the nanoscale communication was envisioned, and for because these devices are very small, you also require very small antennas, which which can which can come which can communicate to each other. So you require a frequency which very small wavelength, and that's how terahertz was also looked at promising candidate as we move to future. So the benefit from terahertz are they have enormous bandwidth. They can support application that require ultra high rates, and they can also coexist with sub 6 gigahertz and millimeter wave bands. And owing to their small wavelength, you can also think about micro or nanoscale communication, where you're talking about communication with devices with very small scale. And again, terahertz also had the same problem as millimeter wave because they kind of lie in the similar bands. But with the recent advancement in device technologies and other commercial technologies, we can expect that terahertz is going to put a pivotal role in the upcoming generation of communication standards. So let us have a small look on what are millimeter wave spectrum. So we know that up to 4G standard, commercial communication was limited to bands up to 6 gigahertz, which we call sub 6 gigahertz, which means below than 6 gigahertz. But there are many frequency bands above that range, which of course, as you go above in the frequency range, your bandwidth increases. And they have been used in variety of non-cellular application. For example, fixed link communication, satellite communication, remote sensing, and some other non-communication applications also. But with recent advancement in antenna technology, we are going to talk a little bit about that. It's now possible to use this spectrum for mobile communication. So this particular band from 30 to 300 gigahertz, with its wavelength is from 1 to 10 millimeter. That's why they are called millimeter wave bands, and they offer hundreds of times more bandwidth compared to the sub 6 gigahertz bands. That was the good part, that they have so much bandwidth, but there are some drawbacks in millimeter communication also. And the two of them are they have higher penetration losses. So as they move in the space, you may expect a larger loss, and they are also suffered by blockages. And these features reduce the signal strength. But there is a good point also with that. These features also reduce the interference from the unwanted base stations or transmitters. So these issues, which we thought about the drawbacks, can be converted into benefit if we have sufficient densification of cells. if you make sure that the signal strength is sufficient by moving the transmitter close to the users, then that is a good point because the interference, which is generally far away, can be reduced by these two features. So because of these two, it's natural that we can use more aggressive frequency reuse, and of course, because the signal cannot go further away, you always have some kind of physical security because of directionality and the higher penetration losses. So millimeter wave frequency from 24 gigahertz to 100 gigahertz, that is the main uh, band which we are looking in 5G. And as we move towards 6G, we have also looking at the bands from zero point 0.1 to 10 terahertz, which we call as terahertz bands. And of course, the lower side of this band is more interesting uh, uh, because as you move above in the spectrum, your challenges increases. So what is the need for this millimeter wave terahertz band? As we discussed, that mobile data traffic has been exponentially increasing. Some noises there. Uh,
Yes, sir. Sir, please continue, sir. It is sorted, sir.
okay. If you have any question, please ask. I will be happy to answer in middle also. And so this is like a standard thing which we all know that when we have these new IoT devices and a variety of application such as supply chains, healthcare, transportation, vehicle communication, we can expect data to traffic to demand to even increase more, right? And there are some numbers here which shows that how they much have increased and how they are going to increase in near future. And to be able to handle this data demand and massive number of these small devices, that was one of the key design goal of 5G networks. So let us look at how does a communication system performance work, right? We're going to look at a particular metric which we call the area spectral efficiency, right? And that shows number of bits transmitted per unit area. So if you have a particular user distribution or a device distribution, uh, then this can also tell you that for each user, how much number of bits you can send. And this metric depends on these parameters. One is log 1 plus SINR, which you know is the upper bound. It's come from Shannon equation. So if you have high SINR, the maximum rate bits per second per hertz you can achieve is log 1 plus SINR. You multiply by this by bandwidth. So you get the total number of bits per second, which you can transmit. Then you multiply by epsilon, which is spectral efficiency. So you can improve the spectral efficiency. This is like how, I mean, how efficient you can utilize the spectrum. For example, if you have more antennas, the spectral efficiencies can be increased by using special multiplexing. And then lambda is the density of the transmitters or the communication links. So if this is per like links per unit area. Sorry. So area spectral efficiency is number of bits per second transmitted per unit area. So include per second also. So if I want to increase the overall area spectral efficiency, what I want to do, what we can do is we can increase any of these things. So for example, you can increase log this SINR, right? But when currently we are moving to interference limited design, which means we do not have a, I mean, scarcity of the transmitter or base station. They are everywhere. They are sufficiently dense, but the problem comes because of the interference from other base stations. So even if you put more base station, it's not going to improve your SINR. So we are kind of done in this part. Bandwidth is the one approach, right? If we just stay in the sub 6 gigahertz, we have limited bandwidth, which we have already used. Of course, we can improve some utilization, but that is not going to be much. Then you have spectral efficiency. The people have worked significantly on different signal processing techniques and a variety of multiple access techniques to improve the spectral efficiency. And the last is this lambda, which can be improved if you do extreme density densification of the cell network. Okay. But the problem is, we have showed earlier that the densification also has a limit. And the reason comes because as you move very close, the interference, you enter into a different near field design, and the coverage starts going degrading in that region. So you cannot get much, I mean, beyond from densification. Of course, these all parameters can help. So the one thing which can give us the order of improvement was this bandwidth factor. What if we move up in the frequency, then you should be able to get a lot of bandwidth. So that's why we said when we move to millimeter wave frequency, the amount of available spectrum was 50 or 100 times more. Normally, we talk about 20 megahertz band in sub 6 gigahertz. Here, you can get around 1 gigahertz or 2 gigahertz frequencies. Yeah, sorry, of bandwidth there. And you note that this bandwidth appears as the pre-log factor in this equation. So assigner, if you improve, that only improves in the log scale. So it's not much gain. But if you can improve B, that directly multiplies the achievable rate. So it can give you a significant improvement in the data rate. Okay. And again, if we can go above, which is terahertz bands, then we can expect even more bandwidth. Right? So here you can expect like uh, around 10 gigahertz or even more bandwidth in these bands. And if things work out, the rest of the problems can be taken care. You can expect around terabits per second in these bands. So of course, we do not want to remove sub 6 gigahertz because it also has lots of benefits. Right? You know that even when we solve many problems in millimeter wave, they are still not very reliable. So reliability comes as we go down in the frequency. So sub 6 gigahertz systems are very reliable and mature. So that is going to be there. But these bands can complement those bands to support the application. And when they don't work, then we can fall back to the conventional sub 6 gigahertz frequency. Okay. So what can these frequency enable other than the data rate? Of course, we know they can support large application, large data rate required application. So of course they can open door for many innovation for it. Uh, but apart from that, they also have some other interesting application. For example, they can act as a backhaul connections between the base station. So you all know that when you connect to a base station, you are transmitting information to base station or base station is transmitting information to you, right? But suppose you want to talk to someone else which is in a different city. So to be able to reach that person, you can contact your base station contact the another base station uh, which lies in the same city as the other person you are going to talk to, and that base station contact that user. So although you are saying only the base station to your link, but there is a backhaul network between all base stations, which takes your information or data and send to the other nodes. And these backhaul connections are generally wired because you require to support a large number of users. And that requires a lot of cost because you have to get the land, you have to install these cables, and especially when you go ultra dense networks, these requirements will keep on increasing more and more. So If millimeter wave can replace these backhaul links via wireless links, we can save significantly. Right? And this can also transform these wired data centers uh, if things can be turned to wireless. Other potential application is in boggy vehicle-to-vehicle communication, which requires low latency and very high data rate. So the reason for this V2V communication is to enable security, I mean safety in the traffic scenario, and also we should be able to tell these vehicles critical updates which can improve the overall congestion of the network. Okay, and of course terahertz can improve further in this. And one thing is also there, we are also seeing a different type of communication. This communication is related to nano machine communication. So you have these nano devices and they want to talk to each other. And because they are very small, the conventional wire RF frequencies antennas may not work because they will make the system really big. So one of the potential way these nano machine can talk to each other is via use of terahertz and uh, via use of this molecular communication. So what happens in molecular communication is these devices can talk to each other with the help of chemical signals. So there is no RF radio frequency involved here. These transmitters are sending molecules which are being received by the receiver, and these can be biocompatible and energy efficient communication, and which we call molecular communication. So terahertz can coexist with this molecular communication to enable overall nano communication. So let us look at some of the bands which are available for millimeter wave. So how do we decide these bands? So know that because of different atmospheric attenuation and propagation characteristics, all frequencies bands are not the same. So you have to choose bands which are good for communication, where the signal can propagate really well. So there is a World Radio Communication Conference (WRC), which generally decides or propose a list of frequency bands. So they have in 2015 they talked about some frequency band 24 to 86 gigahertz, and then some other bands were added in 2019. They also identified a continuous 160 gigahertz band and 250 to 450 gigahertz band in terahertz. So these are some of the bands. I'm not going to go into much details of this. So I'll share the site so you can have a look if you're interested. Mainly the bands which we are looking at around 26, 28, 32, 40, 50, 60, 70, 250 to 296, and 306 to 450. And again, they have some specific bands. And most of these bands may have some incumbent services, which mean they may be already being used for some other uses. So if you want to use this band, they need to either coexist or some need to protection laws need to make so that these application or users can coexist. Okay, so we can see there's a large bandwidth, but of course there are propagation issues also which need to be taken care of. So how do we finally decide this band? That depends on multiple things. Um, uh, there is a requirement that the spectrum should match with their neighboring areas so that there is not interference problem. And then there are, of course, the propagation characteristic, which makes some bands useful than others. So let us look at the propagation at millimeter and terahertz frequencies. And I'm going to talk about basically standard characteristics and how they make things different compared to sub-6 gigahertz. So let us look at first what is different in millimeter wave than the conventional bands. And the first one is blockage. Right. Of course, you can expect blockage anywhere, even in lower frequencies. Uh, the trees and the buildings can reduce the signal strength, but we were still able to receive uh, signal even when we are sitting inside the house. So base station is outside and we are sitting inside with a mobile, but the still mobile is able to get a very good coverage because uh, at those frequencies, the penetration by losses by the walls and the trees are not that much. But in millimeter wave terahertz signal frequencies, they are very sensitive to blockages. And that's why they rely heavily on the availability of line of sight links. So if somehow you do not have line of sight links, then probably the communication may not work because the non-line of sight links have very poor communication, very poor strength. So for instance, you can see that a single blockage can create a loss of 20 to 40 dB, which is a significant loss. You can also see losses from glasses, building materials. Even a single tree can reduce the foliage loss, the loss, the path loss, path signal strength by 20 dB. And apart from that, they also suffer from self-body blockage. So if you're holding a mobile and you are facing away, then the base station, even your body or even the mobile's phone body can reduce the signal strength. So that means even the placement of antenna plays an important role so that you do not see a blockage from the self body. So because these can drastically reduce the signal strength, it is very important first to characterize, understand how these blockages may affect. So the channel model which were devised were actually have to take care of the difference between line of sight and non-line of sight communication. Similarly, we have to also find ways to avoid these blockages. And if a blockage comes, we need the efficient mechanism or processing techniques so that we can hand over to new unblocked loops. So that's a bad thing, but again, as I said, this can work as good also. Along with reducing the signal strength, it also reduces the interference. And we know that in the current cellular network, the main problem is interference because you have enough densification, but because of the interference, your SINA goes down. So if somehow you can reduce this interference, you can still operate in the noise limited design, and there it can improve. So another key feature here is directionality. So the way directionality came was when we talk about the millimeter wave propagation characteristic, we found that if we keep the antenna aperture, if we keep one antenna, the antenna same, then the propagation loss decreases with frequency. So in millimeter wave, propagation loss was significantly low. But then if you keep the antenna aperture same, then you can have more antennas in millimeter wave. So the antennas of millimeter wave is also of the order of millimeter wave. And in the conventional, it was order of centimeters. So your antennas get smaller, so you can accommodate more number of antennas. So with this more number of antennas, you can still get the same propagation, but the communication become highly directional because when you use multiple antennas, these antennas together, they only receive signal from a particular direction. So that's a good thing because it increases the directionality, it increases directional gain. So overall, your signal strength improves. And again, these are formed towards the serving base station. So the interfering base station gain does not increase. So that's a good thing because signal strength increases, the serving signal strength increases, but the interference does not increase. So it's a win-win situation. Okay. But the problem comes with that there are some issues with using very high redirection antennas. First is this deafness problem, which means that sometimes a base station can be here, but you are not able to look at it because your antenna is not pointed. Again, this creates also a problem in the cell selection. So when you are starting the communication, the user has to select or find the base station. Also, the base station has to find the user discovery. So in millimeter wave, the communication cannot occur, even the search communication cannot occur without using antennas. And when you use antennas, you can only look into a particular direction. So to be able to scan all direction, you use uh, more time slot so that you can beamform in each direction and search over that. So that increases your overall search process. And whenever you want to find the optimal beam, also there also you have to search over possible beams, and that increases your latency. And in terms of any incorrectness in the beam selection, your performance can get affected by a significant amount. So it's also important to find about new random access protocols and then this novel adaptive array processing algorithm so that they can adopt quickly to if the link is blocked, and they can also do this beam search quickly. Okay, and the third interesting thing is about atmospheric absorption. So we know that when these electromagnetic waves they propagate in the medium, they can uh, they can collide with the molecules present in the air, and if they are of the same frequencies, then they transfer some energy to these molecules, and because of that, there is some transmission loss which occur at these frequencies. So this depends on the frequency because the size of the molecules and the wavelength need to be of the similar order so that the interaction can occur. Right, and that's why we have these resonant frequencies for gas molecules, uh, which if they're equal to these frequencies, then the absorption loss will be. So in millimeter and terahertz band, because of their wavelength, they are very similar to water and oxygen molecules, and that's why they have very high atmospheric loss because of these two types of molecules. And they are also these molecules are prominent in generally the environment around us. Right, and because of these effects were not much in microwave, so these attenuation further limit the distances millimeter and terahertz can travel. So if they cannot travel fast, you have to put base station closer to the user, and that's a general phenomena which we are looking. It's known as cell densification. You will require more and more cells close to the users. Okay. So now to be quickly understand these channels better, you need some measurements, right? So there have been lots of measurement efforts in these frequencies, which they have focused on characterizing what will be the multi-path distribution, what will be the angle arrival, and other channel parameter distribution. How does the receive signal changes with respect to distance? How does the beamforming works? Right, and some of them are also based on rate propagation mechanism. They also focus on the material losses and the effect of different environmental molecules. So I'm not going to all of them. These are some references you can look at. Um, so people from different areas have talked about scenarios in indoor, such as university, and then they also talk about outdoor environments, right, such as university campus, rural areas. There was in the early days there was two interesting campaigns. One was in NYU and one was UT Austin, where they tried to understand how these channels propagate. People have also talked about the high-speed train channel propagation measurements and how does the outdoor to indoor propagation works. So these, even in terahertz, there are some works where people have talked about indoor and outdoor works and talk how saw what are the interference from unintentional non-line of sight sources. So from these channel measurements, people have come up with key propagation characteristics, that what are the main propagation characteristics of millimeter wave, and I'm going to discuss some of them. As I said, there is something called atmospheric attenuation, which caused by the molecules in the gas. And when they interact together, which will generally happen when the wavelength and the gas molecule size is similar, the there is a transfer of energy from the signal to these molecules, and that's how which this creates in the attenuation of the signal strength. Okay, and this rate of absorption depends on temperature, pressure, altitude, the gas density, right? And this is not much in sub 6 gigahertz because of again the same thing. Their wavelength was about the this molecule size. So here you can see a plot where I have showed the atmospheric attenuation with respect to the frequency. So I have changed from 10 gigahertz to 100 gigahertz. And you can look at these. So this red one is showing the attenuation, and this peaks you are seeing that here the attenuation is large. So whenever the size is matching with the molecule, you see a larger attenuation. And here the peaks are because of O2, here the peaks of S2O, then carbon dioxide on the upper higher frequencies. Okay. Then I also plot the frequency, the attenuation when you have excessive rains or heavy rains or the fall. Okay. So, right, and these of course attenuations are dB per kilometer. Right? So, uh, the attenuation is basically as you increase the distance, the attenuation increases linearly. Right? Similarly, you can observe other peaks on terahertz and the frequency. And sometimes you can see at some particular band, the interference can be really large. So you have to choose those bands in between where the attenuation is relatively low. How we can model this attenuation mathematically? Uh, so there is a law, Beer-Lambert law, which you may have studied in the past. It states that the amount of radiation of frequency f that is able to propagate from a transmitter to the receiver through an absorbing medium, which is like the environment or any gaseous medium for our case, that is defined as which is equal to the ratio of the received power and the actual transmit power is equal to exponential minus Ka phi r. So the r is the distance. As you increase the distance, this attenuation increases exponentially. And this is also a function of f. For this Ka, which we call the absorption coefficient of the medium, that depends on the frequency. And this tau is also called the transmittance of the environment, and it's also a function of distance and the frequency. Okay. So this Kaf depends on frequency as we discussed because uh, it depends where the wavelengths are matching with the molecule size. So at a particular frequency, you look at all the gas constituents which are of the similar size, and you look at their density and type and the probability that they will collide, and that will determine the absorption coefficient at that frequency. Okay. Similarly, you can have rainfall attenuation also because of the similar reason, and the earlier diagram showed you what you can expect in a in a rain condition. Right. For example, a light rain can impose a maximum loss of 2.5 dB per kilometer, where the heavy rain can actually go up to 20 dB per kilometer. So these are actually very high losses, and that makes the communication a little bit unreliable. Okay, but again, if you there are specific brands, for example, in the lower bands, this attenuation was relatively small. Okay, so if we can, this means we have to keep the distances small, and we can the lower bands are much useful for these conditions. By using this, we can reduce the rainfall attenuation. Second thing is blockages. As I talked about, there are various types ways signal can be blocked. One is foliage, where the uh, vegetation or the trees can reduce the signal. And the other thing is material penetration losses. When you are sitting inside a building, the building material can actually reduce your signal strength. Right. And there are some numbers which we already talked about that actually they are very large losses, which limits our the range we can use the millimeter. So the way we incorporate these blockages, we use a line of sight probability model generally in the analysis. These models are very simple. You talk about that there is a link T. So these are statistical model. Of course, if you know the channel, you can, you know the map and you know the everything's deterministic, you can compute it by using a ray tracing. But if you talk about the statistical channel, we take a link of length T and we talk about what is the probability that this link will be blocked. So there are various channel models given to characterize this line of sight probability. So here, for example, you see the line of sight probability of a link of length D in an urban macro cell scenario is given by this particular format where these D1 and D2 are different parameters. And in particular case, they are found to be 18 meters to 3 meters. So you put the distance, it will tell you what is the probability that this link will be blocked. Similarly, you can change different scenarios and these parameters can change to compute the blockage probability for various other scenarios. For example, urban microcell or rural cell, indoor cells, and like that. For example, this is another model which is given by NITR with different parameters of different. These models are not just empirical, there is also a theoretical guarantee which exists. Via the use of stochastic geometry and random shape theory, you can show that if you have a network with random rectangular blockages, then a blockage, a link is blocked, is given by e to power minus beta d. D is the link distance, and beta is this parameter, which depends on the average width and length of the buildings and the density. How many blockages are there in a unit area. So, which is very similar to the actual equation, which shows that the blockage loss is actually decreasing exponentially with distance. So, as you increase the distance, your blockage probability can reduce significantly. Okay, and there are other different models also which are taken, which I'm not going to cover, but there are other theoretical and experimental based blockage model which characterizes this line of sight probability. And once you know the probability, you can actually have a guess that what is the chance that if I have my transmitter and receiver in a particular distance, what is the chance that this link will be blocked or not. Right. Apart from this foliage losses and the penetration losses, you have other blockage in millimeter wave, which is human shadowing and the self blockage. So your own body can reduce the signal to your own mobile. Even the mobile body can also reduce the signal strength to itself. So there are various ways these can be modeled because the humans can, or if you look at in pedestrian settings, human can human can move uh, and can be modeled as randomly. We can think, we can see model them using a random point process, which are like a Poisson point process, where you can think each human as a 2D circle or a cylinder, which is distributed in a 2D space randomly according to a Poisson distribution. Okay. Similarly, cell blockage, you can model it. So if you put a phone in front of you, uh, so you are here and the phone is here, you can think that all the base stations which are behind this phone will be blocked. So you see a cone, a 2D cone here, all the base stations which will lie in this cone will be blocked. So people can have used this cone-based model to model this self blockages. Okay. Now, other interesting fact is about reflection and scattering. So, any question up to this point? Okay. So, Dr. Pankaj, can I take a 5-minute break here?
Sure, sir. Sure, sir.
Okay. So I'll just come back in 5 minutes. You can guys can also take a break.
Yes. Dear participants, please stay in the meeting. Sir will be joining again within 5 minutes.
Hello, I'm back. Can I start?
Yes, yes, sir. Please continue.
Okay. So now there is another phenomena which we observe here is related to reflection and scattering. So suppose there is a wave which is falling on a surface, and if the surface is smooth, then you see a single reflection in a certain direction. So that's how you normally see in light, and that is similar in other EM waves. And the fraction of the incident field that is reflected in a particular direction, that power ratio or signal ratio we denote by the reflection coefficient gamma s. And there's some loss, which say some signal which is lost in this reflection. So because of that, you have some reflection coefficient. So if you have an incident wave here, and this reflects back the same angle, the received power, sorry, the reflected power is given by the transmitted power into gamma s squared. So this is when the surface is smooth. Now, if the surface is rough, right, the wavefront which is falling in this does not observe a smooth surface here. So that's why it doesn't get reflected into a particular direction. It also gets reflected to in a variety of direction, which we call scattering. Okay. So this phenomenon is known as diffuse scattering, and which is also observed by in millimeter waves and terahertz networks. So here the key point is whether the surface is smooth or rough. And it turns out that it actually depends on how waves see it. Right? So it depends on the wavelength. If your wavelength is small, the small defects in the surface will make the surface rough. And if the wavelength is large, it doesn't observe these small differences, and that's why the surface will look smooth. So whether a surface will be perceived smooth or rough, that depends on the incident wave properties. There is a criteria which we call Rayleigh criteria, which can determine the smoothness or roughness of the surface. So for each wave or wavelength lambda and incident direction lambda I, the critical height parameter is given by lambda by 8 cos theta. So this is corresponding to the wave. It depends on the wavelength and the incident direction. Now this is a small value because lambda is small. This is the critical height. Similarly, for the surface, though this is the HC is the parameter to the wave, then for the surface you have a parameter called H0, which is called the minimum to maximum surface protuberance. Okay, so look at how the surface is varying, and overall the mean or to maximum difference between the surface, which we denote by H0, and the total variation in the height is denoted by HRMS. Now you compare H0 by Hc. If the surface disturbance is less than the wave size, wave critical height, then the surface will look smooth. And if the surface disturbances are more than the wavelength parameter, then the surface can be considered the rough. Okay, so as lambda decreases, the same surface which were earlier smooth at higher lambda now become rough. So that's why at lower frequency, your reflection phenomena is significant, while scattering is negligible. Right? As most surfaces look smooth compared to the wavelength. But as you go higher frequency, your wavelength decreases and the surfaces looks rough. So in millimeter wave band, lower bands, reflection are still more prominent, scattering is moderate. But as you go in higher to higher millimeter wave bands in terahertz, the scattering becomes significant. as the roughness in the surface of buildings becomes comparable to the carrier wave. Okay, so that's why terahertz frequency, the scattered wave is significant, and that's why it need to be included in the analysis. So because of this scattering, you have additional loss in the reflected wave. So if you suppose the scattering loss factor is rho, right, then the actual reflection coefficient becomes rho times the gamma s. So this rho is less than 1 because there is some loss. So that's why the reflected coefficient is actually lower than the reflection coefficient of the smooth surface. And this rho is actually given as by the surface disturbances, wavelength, and the incident wave. Okay, and again, you can see that if the sorry, yeah. So and then the scattered power, whatever is remaining is the scattered power. So if the total transmit power was P, incident power is P, you divide 1 minus rho square into gamma square. This is the remaining power which was scattered. Okay, and the reflected power was P rho square gamma s square. Okay, so the original power which was P gamma s square was divided now into two parts, which is reflected power and the scattered power. And the fraction of the power which is reflected is denoted by s square. Okay, so the scattering coefficient s square is given by the scattered power divided by the incident power. And if you look at this equation here, if you divide ps by p, you just get 1 minus rho square into gamma s square. So this depends on the smooth surface reflection coefficient and the scattering loss. Now this is a scattered power, but this scattered power actually uh, gets scattered into all directions. So reflection only gets scattered goes into a particular direction, right? Where the angle of the incident and the reflection angle are same with respect to a normal, but the scattered power can be in any direction. The way you people have modeled this scattered wave is there are different models. One is directive scattering model, which says that in the scattered power is highest in the reflected wave direction, and it decreases on the both sides with this formula. So theta s is the angle from the normal. So scattered power in the direction theta s is given by 1 plus cos theta s minus theta r by 2. So when I put theta s equal to theta r, I get the maximum value. And then in other direction, this slowly decreases with a cos function to the power alpha r. Okay, this alpha r is the width of the scattering lobe, and it again depends on the material. So people have used this scattering model to model the propagation at different cases. For example, in a hospital room at 60 gigahertz, and for rural or suburban buildings at 1.29 gigahertz, and they found this model actually works good with measurements. So now, once we know the scattered power, let us compute what will be the scattered power at a receiver at Ri distance. So we all know this Friis equation, right? Friis equation tells you what is the power loss at some distance. So if you have a transmitter at Ri distance, the incident power will be given by Pt Gt upon 4 pi R square. Okay. You multiply by this by the scattering aperture, the size of the scattering body, which is AS. So AS is the effective aperture of the scattering surface. You multiply by the power density, and this you get the total incident power. Okay, so this is this part AS into Pt into 4 pi R square is the incident power. Now you multiply by the S square, which is the scattering coefficient, and you get the total scattered power Ps. Okay, so that is the total power. Now using this DS model, you can say in a particular direction theta s, the scattering power is given by. Okay. Now we can now, to compute this PS0, we can normalize it. We can integrate both one with respect to theta s and make it equal to the total scattered power PS. So when you do that, you get the PS0 should be equal to PS by this. And I put this thing back to the original equation to get the total received power at the receiver located at angle theta s and at distance rs is given by PS theta s into effective antenna aperture. And the effective antenna aperture we know is given by lambda square upon 4 pi into GR. You multiply by that PS, we already know the formula. So this will be the scattered power. So let's look at this equation. This depends on the scattering coefficient S square, the size of the scatterer, the transmit power and transmit gain, 1 upon the distance between the transmitter and the scattering object, and the distance between scattering object to the receiver. Lambda square upon 4 pi, which is the effective antenna at the receiver, which depends on lambda, received gain at the antenna, and then some normalization coefficient, and then this is a function of theta. You can also extend it to model for the back study. Okay, so this is the additional scatter power which we need to include along with the normal reflected power and the signal power. And then there are other small factors like diffraction. We observe that millimeter terahertz, the diffraction is not that significant. Similarly, the Doppler spread will be very significant in millimeter wave, right? Because the Doppler spread is directly proportional to the frequency and the speed of laser. So if you go above in the frequency range, your Doppler speed will increase. Then you have absorption noise. Right? So what is absorption noise? What happens is when the wave propagates, these molecules can absorb the signal by colliding with them, and then which causes a vibration, and because of that they themselves can emit electromagnetic radiation at the same frequency. Okay, so they absorb the signal from the transmitted signal or already present signals, and then they emit that, and because of that this absorption can also provides additional noise, which we call the absorption noise. So we need to include this factor again in terahertz bands, so that the effective noise increases other than the Johnson-Nyquist noise. Okay. Then there is another factor which we call scintillation effect, and that causes because of the rapid fluctuation of wave phase and amplitude due to fast local variation in the refractive index of the medium. Okay. So people have also talked about this scintillation effect, but how it will exactly affect the communication is not exactly well known. Okay, so now let us look at how a particular propagation factor, which is beamforming in antenna patterns. So we all know that beamforming means you have multiple antennas, and using these antennas, you can modify the signal such that they're only received or transmitted in a particular direction. Okay, so normally in a omnidirectional antenna, the power is spread in all directions. But using this beamformer, you can send power into one direction. So this saves our energy, and it also helps us get again into a particular direction while not causing interference to other base stations. Okay, so the gain that's achieved in signal to noise ratio by this beamformer is known as beamforming gain. So traditionally, people use distal beamforming, which means that you take the signal, you receive the signal, you convert to distal domain, and there you apply the receiver beamforming. Similarly, at distal and when transmitting the signal, you do all the processing at the distal side, right? When you have IQ symbols, then you use the RF chain to convert it to an actual physical signal. Now, this means that if you have 6 antennas, you require 6 different RF chains because you need to be able to modify each of the signal which are being sent to each of the antennas. So now this fully distal waveforming is not suitable for millimeter wave, right? Because in millimeter wave, we may be talking about 64 antennas or 128 antennas, right? And these antenna size is small, so they can be kept in a small distance, so keeping is not a problem. But when you have so many antennas, if you try to have one RF chain for each of these antennas, that will result in a huge power requirement, right? And that may not be feasible because the power consumption increases linearly with sampling rate and exponentially with the number of bits. So what we want to do is instead of having this distal beamforming, we move to analog beamforming. So in analog waveforming, what happens is these are different antenna. The signal comes in analog itself. They multiplied by some phase shifters. So these are phase shifters. Each of the signals phase is shifted and then combined together. And then that is crossed through RF chain to convert to the distal signal. Right now, by varying this phase on this phase shifter, you can change the direction of receiving all the transmitter from this. So this is known as the analog beamforming, okay, and which is achieved by a phase shifted array. The problem is you cannot do this RF distal beamforming or distal processing here. So the whole thing is applied together to all frequencies. So you cannot have single stream or single user transmitter option. So a middle way where you want to have multi-user, multi-stream also without using that many chains, what we do for hybrid beamforming, you divide the number of antenna into small groups. Each group has one RF chain, while this all the antenna in that groups are only connected by the phase receivers. And then you can also have different architecture. For example, you can connect all these antennas together, or you can connect them partially, right? And this hybrid beamforming provides a trade-off between the low complexity but restrictive analog beamforming. Okay, so the analog beamforming is low complexity, restrictive, but distal beamforming is highly complex but more flexible. So you choose a middle way. You choose some flexibility and some complexity to get the hybrid beamforming. Okay, so right. So then you have the way the benefit is analog beamforming. The effective gain can be denoted by the antenna pattern. So you can have a particular transmit antenna pattern, and using that you can compute the gain in the direction of a particular arrival or the departure of the signal. So based on different antennas, you have different analog pattern. For example, if you use the uniform Lydian array, the gain is given by this function, which is a function of the angle and number of antennas. Then there is a simplified antenna model which can be used for analysis, which is known as the sectorized antenna model. What we do here is, this is the actual blue is the actual beam pattern, but we model that beam pattern using a sectored approximation. So we assume that in this particular angle, theta, the gain is maximum, and the rest of this direction, the gain is smaller. Okay, so here you can denote the gain into direction theta as gm if the theta is between these two in the beamwidth and small gs if otherwise. And then GM and GS is known as the side lobe gain and GM is known as the main lobe gain. Okay. Now, in high dense network, your interference from side lobe can also be significant because there are significant number of base stations. So we have to include the interference in both lobes, and we cannot ignore the interference in the side lobe. Okay. Then this is a single lobe approximation. When we go for multi-user, right, because of hybrid beamforming, you may see antenna model which has multiple lobes, multiple main lobes, which you can model again using the sectorized approximation with k number of lobes with a constant. Okay, so this kind of work has been done for different analysis. Right. And people have talked about different DNA models which you can use for different scenarios. Okay. Then there again is Gaussian cosine antenna models which have this particular antenna pattern which can be used. Okay. So alpha distribution can be extended to include hybrid beamforming supporting multi-stream multi-layer transmission. As a layered technique, hybrid beamforming can be seen as the combination of distal and analog beamforming. So the effective antenna pattern in the case of multi-user and multi-stream transmission will consist of individual analog beam patterns overlapped on each other. Okay, and each analog beam pattern is one stream or one. Okay. Similarly, for terahertz beamforming, you can even put more number of antennas. So we can talk about very dense, ultramassive MIMO antenna systems, and as the size is small, they can fit into a very small footprint area, right? So they can accommodate a very large number of antennas. And as the number of antenna increase, you can actually get very, very narrow beams. So which people call as pencil beams because they are as narrow, can be as narrow as a pencil. So this will increase into very high gain. Okay. And again, with terahertz also, if you try to put RF chain into each of the this will not be possible. So people are again talking about hybrid analog beamforming for the terahertz networks. Okay, so which can provide a very better trade-off for analog and digital methods. Right, and terahertz, the type of antenna that can be used are photoconductive antennas, horn antennas, lens antennas, microstrip, or on-chip antennas. Okay, so let's look at quickly at the complete channel model. So what does channel model means? That you want to characterize what will be the receive power of a particular link, right? If the link distance is given to you. And we're talking about statistical model. So we are not talking about a particular map. We are talking about a general like a outdoor setting, what you can expect in a typical communication system in an outdoor setting or indoor setting. So to be able to evaluate the performance of any communication system, we need channel model, right? We need to be able to know how each links work. And people have used different channel models, both from analysis or simulator. So from analysis side, the channel models are a little bit simple because you want the analysis to be tractable. While in simulator, you can actually go for complicated channel models. So the METIS proposed 3 channel models, namely stochastic, map-based, and hybrid models, where stochastic model is suitable for frequency up to 670 GHz, while the map-based model is applicable to 100 GHz. Similarly, 3GPP channel and NYU SIM by NYU was also released for millimeter wave bands. For MIMO model for terahertz, you can have matrix-based model or the reference antenna-based models. So I have listed the references where you can look at these models in more carefully. Here we are going to talk about simple analytical models which can be easy to understand and are still tractable. So in millimeter wave, these models should be able to take care of antenna gains, directivity, and the blockages. And terahertz, along with the other two factors, this model should also be able to take the absorption loss. So, right, let me talk about very quickly because the time is running out. Let me go through quickly with a millimeter wave channel. So suppose a link between a transmitter and the receiver is located the R distance is of type S, which means it can be line of sight or non-line of sight. So I call link to be L, which is line of sight, and to be non-line of sight. Right, and we are going to assume analog beamforming here. So here for a particular ring, the receive power is given by this particular formula. So let me explain these terms. PT is the transmit power. LSR is the path loss at the R distance. So this is the average loss in the signal power at distance R. And this depends on S, whether it's a line of sight or non-line of sight component. A very popular model to model path loss is the power law, where you assume that with distance R, the power decreases as CS into R to power minus alpha S. R is the distance. Here CS is the near field gain and alpha is the path loss exponent. And these are different for a different line of sight and line of sight links. Then GR theta is the antenna gain from the receive antenna gain in the direction of theta. Okay, theta is the angle of the angle of arrival at the receiver, or in a very single path communication, you can think of this as the angle to the base station. So this and then G T theta, theta T is the departure angle, G theta is the transmitter gain in this direction, and H is the small scale fading. So normally in millimeter wave, the H can be taken as in fading can be taken as Nagami. So with different parameters for line of sight and non-line of sight links. So therefore H will be a gamma random variable with parameter mu L or mu L. Okay, then you can, this is a very simple model, but you can include, extend this model for different environments and propagation condition to include multiple parts, multi-rank channel, hybrid beamforming, and massive beam. Okay. Now in Terahertz channel, you have to also include atmospheric attenuation and the scattering. So we have here the for receive power is again given by a similar equation. Only thing you can see is there is additional factor tau r. Okay, and tau r is due to additional loss due to molecular absorption, and we have already gave its equation in terms of r and frequency. Okay, for line of sight links, the path loss can be given by this factor. This is same as the previous one with alpha, the path loss exponent as 2, and the near gain is given by this. So this is Friis equation which define the free space path loss, and which you can include you can extend to include scatters and. So now if the R1 is the distance between transmitter and the surface, and R2 is the distance between scatter and receiver, the scattered and reflected power are given by this. So rest is same, only thing the difference is you have a gamma R here and the absorption coefficient for these two links. Similarly, for reflected power, because of in the reflection in spectral direction, you have a path loss in R1 plus R2 direction, and again attenuation also in R1 plus R2. So scattered power and reflection power are inherently different. Okay, and then of course you can extend this for more complicated scenarios. So here I just try to give you a very simple analytical model which we can use to compute a tractable, simple analysis for that. Okay. Now I am going to talk about some this thing quickly. In millimeter wave communication system, what you can expect, right? So we saw that they are susceptible to blockages and foliage loss. That's why you need directional communication. But these high signal attenuation and directional transmission have advantages and disadvantages both. Right? Disadvantages because it reduces the signal power, so you can only operate in a small distance. But they also reduce the interference. So you are going to operate in noise limited design, so you can get better deterrence. So what you can expect in a communication molecular communication system, sorry, in a millimeter wave communication system is very small range. You need very densified networks. And the good thing is, because of small range, you should be able to reuse the frequency. You should be able to let two devices operate at the same frequency without interfering each other. And that also gives us a concept of spectrum sharing. Right? Normally, if you want to share the spectrum on the same frequency, you need a lot of coordination. You need to either let them, each of these devices only operate at one of them by using some tokens or doing some coordination. But in millimeter wave, because of these highly directional beams, it turns out that you should be able to use, right, right, you should be able to use these networks without any coordination, right? You can of course do some coordination which can help, but even without this coordination, you should be able to use these networks. So that's why spectrum sharing mechanism in millimeter waves is an interesting area, and we can expect that the licensing in the millimeter wave would be much more dynamic to allow such kind of uh, optimal utilization of the spectrum. Second thing, as we said, even though they provide good data rate, they are still unreliable. So to have some reliability, you need to put them together with the lower frequency systems like sub-6 gigahertz. So whenever you require high data rate, you can use millimeter wave. But when they are not available, you can always fall back to the sub-6 gigahertz. You can also use this sub-6 gigahertz to have a more control channel type of application. Also, since the blockages can happen every time, you can also use macro diversity application where you can keep more base station, millimeter wave base station ready in case one turns off. You can use them to you can do an immediate handover to another. Okay, then you will, because the low range, you will expect an ultra dense network, which means the base station will be very close. Uh, As the number of antenna increases in a high mobility scenario, probably the conventional techniques may not work, so you will require more complex beamforming predictions. For example, you can deploy deep learning based beamforming schemes to predict what kind of beamformer would be required in the next time slot, depending on the previous time slot and the general perceptions from the local environment and other sensory data. Okay, then you will have other applications from millimeter wave. For example, you can talk about 60 gigahertz unlicensed operator using different area networks. There are also different standards made uh, around these frequencies for millimeter wave to be able to support high data rate and various application of millimeter wave networks. As I said earlier, you can also use millimeter wave to provide backhaul infrastructure. So that's another application where millimeter wave can be seen to be used. Okay, I'm going to just skip some of these to save some time. Then I'm coming back to terahertz communication. Again, terahertz communication will almost have same challenges and implication which millimeter wave. Right? Apart from that, there are some other factors which we can see. One is it will again have even a smaller range than millimeter wave. Sometimes you can see that it can only provide coverage up to 10 or 20 meters. Then another factor is how the you can design transmitters, right? Because to be able to use these terahertz, you need to be able to use a larger bandwidth in transmitter. You need a transmitter which can support wideband, and that's why it's an interesting field where how you can optimally design terahertz receivers. Again, as the beams are very small, you need to constantly track these beams, uh, as you cannot perform the beam forming every time you require it because it takes a lot of time. Then what are the key application? In key application, you can expect that terahertz are more likely to be deployed for indoor applications, and yeah, for a small coverage in high directionality, it is expected that similar to millimeter system, terahertz can efficiently share spectrums. Other application, potential application of terahertz is in macro. So one is in microscale terahertz communication, where it can be used for as conventional communication applications. But then another application is in micro nanoscale application, which we talked about the molecular communication. It can be used for health monitoring. So they are nanosensors which can be put inside human body to measure the different level of different pathogen and vital components. And then they can interact with these terahertz systems to transmit this information to outside devices. Then you can also use these nanosensors to sense harmful chemical molecules in the environment, and then they can coexist with terahertz to collaborate this information together. Okay. So that's why this concept of nano network comes, which is a combination of molecular and terahertz networks, which enable communication between these nanomachines. So I'm not going to talk about this much. I'm just going to skip. When there's some standardization effort, which I have listed in this slide, which you can have a look over. So this just shows that what are different standards which can become sorry. So terahertz, up to now we have only talked about research activities. Once to enable to into commercial application, you need to standardize it. You need to standardize different aspects of the network. That's where this standard scheme. So there are various standards which we have talked about for millimeter wave. Um, uh, I have to skip that because of time here. So now let's come to the conclusion. What we saw that one of the interesting factor about 5G communication is the introduction of this millimeter wave. Right? Up to now, we have talked about a lot of different techniques and improvement, but we stayed on a similar frequency. In 5G, we proposed and made this reality to use millimeter waves. Right? And this not a simple task. There were many tasks, many factors which made this reality, including the advancement in communication and devices technology. Now, as we move forward, we have to look at more ways to improve the frequency, so data rate more, because the application will keep on improving, and you will see applications which are even more data hungry. So that's why people have started looking at higher frequency than millimeter wave, which lies in the band of terahertz. So in this talk, we talked about uh, the importance of this millimeter terahertz bands. We looked at their propagation characteristic, channel models, and how these propagation characteristics affect the design consideration and the implication of these systems. We also looked at some potential applications for 6G and beyond for this network. So that's all I'm going to cover today. So please ask any question if you have. I will be happy to answer them. And if you want more to know more about this, you can always refer to the book chapter I gave you in the starting, which discuss these things in much more detail. So please ask any question if you have.
Thank you, sir. It was really a nice talk. You have covered millimeter wave communications and terahertz related communications in greater detail. And I hope that participants are able to understand the technicalities of these new type of communications. So participants, you can ask your question directly by enabling your mic, unmute yourself and then ask the questions. Any questions from the participants? Please unmute your mic and then ask the question. Okay. Sir, I have a question. We are having millimeter wave and terahertz communications, and as we have seen that this is applicable for short distance communications, because on ground we can see that there are so many blockages. So this is detrimental for this kind of communication. Let us see. I would like to ask how this spectrum can be utilized for inter-satellite communications, or from satellite to high altitude platforms communications, or from satellite to UAV communications, because there is only the atmosphere in between, but there is no blockage. And one more thing, what is the applicability of terahertz spectrum for the communication between satellite and the node such as UAV, which is lying below the troposphere? So what kind of absorption or losses that will occur in this kind of system? Sir, please enable your mic.
Sorry. So yeah, first one is this, that even with these blockages, you can think about scenarios where you can use the millimeter wave. For example, there is an interesting problem to provide coverage in a stadium. So nowadays, you know that when you go for to see a match, cricket match or any match, you just don't watch the match. You also want to, provide a coverage of that to your friends. You make videos which you want to send to others, and you want to also make a video call. I mean, somehow you want to be connected. You want to remain connected while watching the match. And this means if you can think that there is 20, 30,000 people in that stadium, that creates a huge data demand in a very small area. So they are mostly fixed because these users are settings, so they are not moving that much. So in these stadiums, you can deploy millimeter wave base stations very closely, where they can provide very good coverage, coordinated beams to these networks. So that is one application where the blockage does not really play a role because everything is close by and you're talking about a setting. This is one application where the sub 6 gigahertz may not work because this frequency is not able to support these many users. Right. So you're going to see this kind of more, networks, like you are talking about indoor, or for example in a city, right? If you're a big city, there is a straight road, so there is no blockage, but still you're going to talk about this. So that's for conventional one, and then you're talking about the satellite one. So these links are already in use. So people do talk about this Earth to satellite terrestrial links where they can use this communication to use. Then you also have a high altitude communication between. So if you talk about this backhaul links, right, you can make them at some heights, and instead of being connected via the wires, they can be connected via millimeter wave links. Okay, so if there is no blockage, they can actually go for with a suitable antennas, right? So you can have this data backhauls, sorry, base station at a very high, and they can talk to each other without any blockages. So you can think of scenarios where there is like they can be line of sight communication and very high need of data rate where you can use that. Right. As far as Terahertz is concerned, uh, I'm exactly not sure about their. We have to do a link digit analysis to know whether these links would be feasible or not, right? Because the terahertz involve frequencies from uh, in a wider range, right? So not all frequency will work. Of course, when you go for lower side frequencies, you can you can expect them that these frequencies may still work. So right. So this is currently a proposal for available bands, and you can see that these small frequencies like 26 gigahertz and 28 gigahertz, you can see that they already have application where they are talking about fixed satellite Earth to space services, high altitude platform services applications. So these are currently incumbent on that. And as we go upper in the frequencies, probably people have not focused much, but there is some early proposals for land mobile and fixed services, and people can use for outdoor. And then again, as you go above, you can talk about short range communication, right? So UAVs would be similar problem. The thing is, if UAVs are moving, then you would require a some system or some tracking system where you can change beams quickly, right? Because otherwise, if they are fixed, then things are fine. But if they are moving, you have to think about how you can modify these beams very fast.
Yes. Thanks for the explanation, sir. But there is one concern. We are having inter-satellite links and satellite to HAB links with millimeter wave bands. That is working fine because these HABs are in general deployed above the troposphere. But here the UAVs are low altitude platforms which are below the troposphere. So when what is the effect on this millimeter wave propagation when these kind of waves pass through the troposphere? This is the main concern with the low altitude platform. What kind of losses will occur with this?
Yeah, I've not actually looked at carefully in these particular scenarios. Right. My understanding would be that if you can get a line of sight somehow, right, will work. The problem would be that you need to be able to make sure to track the beam constantly, right? So if the things are moving, you need to move the beams because these long distance communication with millimeter wave depends mainly because on the directionality, right? So if you can keep the directionality, things may work.
Thank you, sir. Participants, any other questions? Please ask.
Yeah, yeah. Thank you, Abhishek sir, for such a good session and good morning. Sir, I have a question that we have seen the Starlink project from the Elon Musk. They started working with this and giving a very good internet service, even though in the Ukraine. And same on the other hand, China has the concern, military concerns regarding this. They raise the questions in the United Nations also. So what is the future of this type of communication, means satellite to user? If we discuss about the point to point communication with the these tetra hertz communication, and we go beyond these, we can think about the satellite to industrial communication via direct link. So what is the other concerns? I'm just asking regarding to the securities, because it is going to be a very big business in the future and definitely very big concern for the each and every country. So what are the challenges we have related to this point of view?
Um, So yeah, thanks for him. So I may not be able to comment anything other than the technical part, right? So there's a lot of see with spectrum and with spectrum regulation, with technologies. There is a lot of political and other concerns, right, which need to be taken care of. But I can only comment of technical point of view, right, because that's hard to think about. So I may not be able to help you in that. But technically, these are very interesting applications, and I may see a great future in those. Rest, I am not sure about what there will be political and security concern about that.
Okay. Sir, is it possible for go with the point-to-point communication with the terahertz waves?
So I say it again.
Is it possible to go for the point-to-point communication with the terahertz spectrum?
Again, terahertz spectrum is a very big. So
Okay.
we have to talk about which particular bands we are talking about. Different bands will have different application. But in general, yes, it's possible to go for a point-to-point communication, right? While maintaining the line of sight content, right? Another application would be, see, these nano networks, when you talk about, these are again point-to-point communication, but on a very small scale. So these nanoscale devices cannot accommodate larger antennas because they're very small, right?
Mm.
So if you want to put antennas in that, you want to go for a higher frequency. That's why terahertz will be in picture. You can put them, they can communicate with each other, and that's another application. So those are point to point in a very small range.
Okay.
Okay, and again, you can talk about large range, but again, you need directionality and line of sight there.
Okay, sir. Thank you. Thank you, sir.
Thank
Any other questions from the participants? Please unmute your mic and then ask the question. All right. So thank you once again, sir, for accepting our invitation for this talk. You have elaborated millimeter wave and terahertz communications related aspects to very in detail. And I believe that this talk is going to be very useful for the participants who are working in this area and looking for future research in this particular area. So thank you very much, sir. Thanks for your presentation.
Okay, thank you for inviting me. If you have any further question, you can participant can email me also. Okay, and you can also refer to the book chapter I gave you if you have any want to learn about something as to which is not covered today. So thank you.
Thank you, sir. Thanks for
Thank you,
joining. Okay, so participants, now we will close this session. And we will be joining again, as you have seen that Professor Gupta has highlighted many times the nano networks, nano machines, biomedical things. These are related to molecular communications, where the communication takes place without electromagnetics. It will be the communications through chemicals. How this kind of communication is playing an important role in healthcare, and it is it is an emerging area of research nowadays. So I request all of you to do join the next session by Dr. Satish Kumar Tiwari. He is from SRM University, Andhra Pradesh. He has done a lot of work on molecular communications. And we will be meeting for this session at 11:30 a.m. And please join this session. So thank you all for attending this session. I'm closing this session now, and we will be meeting again at 11:30 a.m. Thanks for joining.